Hello, everyone. Thanks for coming. Before we get started, well, let me introduce myself. Yeah, I'm Rafael, and I work in the JavaScript Foundation team at Facebook. Our team is in charge of a bunch of core tools for JavaScript developers, and some of them are open source, like, for example, Yarn, Jest, or the Metro, which is what I'm going to talk today. Metro, sorry. Let's just start with what is Metro. If you have been developing React Native apps, you have probably seen this message before. This is Metro. It is a JavaScript bundler. In other words, it's a tool that takes a set of JavaScript files, like the code base of your React Native app, and generates a bundle that can be run in many devices. Metro is commonly used by React Native. It is the default bundler shipped by the framework. And in fact, it has some unique features targeted to it, for example, to improve performance. There are many bundlers out there, so why do we need another one? The most important reason is speed. Our goal is to provide sub-second reload times, and we have invested a lot of effort in Metro performance, to be able to achieve this. We also need a build system that is not only fast today, but also tomorrow. At Facebook, our React Native code base doesn't stop growing every single day. So we need to make sure that reload times stay constant, no matter the size of the code base. The last reason is to have a build system that is deeply integrated with React Native. In that sense, Metro provides some features that are crucial for React Native development. For example, the remote debugger, hot model reloading, or the generation of assets. After this quick intro about Metro, let's see how a JavaScript bundle works. This will later help us understand how Metro works. What you can see here is the anatomy of a basic bundle. The first thing is the runtime, which takes care of making dependencies between the modules work correctly. Then we have the list of all the transpile modules that form the application, one after the other. And at the very end, we have the startup code, which bootstraps the whole application. Now let's dive it a little bit into these pieces. The runtime is the core of the bundle, and it contains the glue to make the whole application work. It's in charge of two main things. First, it has some logic to register the module. This is what we call the define function. It also implements a require function, which handles the loading and evaluation of modules. This is what makes imports or require statements worth finding inside the bundle. Let's look at the actual code of the runtime. First, the define function. Internally, we call this __d. This is to save some bytes, because this function is going to be called for every single module in the bundle. It has a couple of arguments. The first one is the module factory. This is a closure that contains the module source code. And the second argument is the module ID, which is an identifier for the module within the bundle. This could perfectly be the module absolute path, but instead Metro uses numerical IDs. This is, again, to save some bundle size. In terms of logic, this function doesn't do much. It just stores the module factory inside an internal object. Along with this factory, there are a couple of parameters, which is loaded, which is a Boolean, and it's used to know for the require function if this module has been already evaluated, and module, which contains an exports key, which is used for caching the exported value of each module. Now let's look at the require function. This one is called __r. In this case, it's not only to save bytes, but also to not clash with other potential require functions that might exist in the global object. For example, if we want to run bundles inside Node.js environments. This function has a single parameter, which is the module ID. The first thing that it does, it checks if that module has been already registered in the bundle. In case that it hasn't, it will throw an error. Then it checks if the module has been already evaluated. If so, it will return its cached exported value. This is to not evaluate modules more than once, as the standard mandates, even if they are required multiple times. Then we evaluate the module. We do this by calling the module factory. And we pass a few parameters here. First, the global, which is a reference to the global object. So modules can access the global object. The second thing is global.__r. This is a reference to the same function. So modules can require each other without issues. And then we pass module and module.exports. This is typically used by modules to export values. The last thing of the require function is to return the module.exports, which basically will return the exported value of that module. So that was the runtime. Now let's see how the actual models get included in the bundle. To include a model, it has to be registered into the runtime. And for this, we call the __d function, or the define function that we have just seen. So the first thing that we do is to wrap the whole module source code inside this __d function. As we saw, this function accepts the first argument as the model factory, which is disclosure, again with the same arguments, global, require, model, and exports, and the second argument being the module ID, which is auto-generated by Metro in an auto-incremental way. Also, note that requires statements that are found inside each module gets transformed. So instead of having paths here, they get transformed to be module IDs that correspond to that same module. The last bit of the bundle is the startup code. This bootstraps the whole application. Up until now, the bundle didn't do anything at all. It just registered the runtime and all the modules one after the other. And as we saw, modules are not evaluated until they are actually required. So we need to require the entry point in order to start the whole application. To do so, we call the require function, or __r, passing the module ID 0. This is because Metro generates this auto-incremental module IDs starting from the entry point. So if we put all this together, this is how the contents of a very simple bundle with just 2 modules would look like. At the left, you can see the runtime, and at the right, the 2 modules concatenated, plus the startup code. A small disclaimer, though. What I showed here is a simplified version of the runtime. The Metro runtime has a little bit more logic. This is to handle some edge cases in the standard, like circular dependencies or modules that throw errors during evaluation. It also has some additional logic to make development easier. For example, to show better error messages or to handle hot module reloading. Now that we have a better understanding of JavaScript bundles, let's see how Metro builds them as fast as possible. The bundling process, it's done by Metro to be able to build the bundles. And this is split into 2 different phases. The first one is to generate the dependency graph. This phase takes the entry point of the bundle as an input and produces an object containing the whole graph of dependencies. This graph object contains the transform code on the source map of each of the modules, and all the relationships between them, the list of dependencies for each module, which are the requires, and the list of inverse dependencies, which are the modules that are requiring that module. The second and final phase of the process is the serialization of the graph. This takes the graph object that we generated in the previous step and generates a string or a buffer or anything. There can be many serializers that apply for the same graph. For example, in React Native, we use 2 different serializers when building the production apps. One for building the actual JavaScript bundle, and another one for building the source maps that correspond to that bundle. Let's talk a little bit about the generation of the graph. During this phase, Metro does 3 things. The first one is to transform each of the modules. This way, all the new JavaScript syntax, for example, the JSX tags on React, get transformed into code that can be understood by any JavaScript virtual machine. To do so, Metro uses Babel. The next thing is to find the module dependencies. Here, it looks for require or imported statements that are found in the module code. This way, Metro can discover all the modules that need to be included in the bundle, and therefore in the dependency graph. The last bit of the process is to resolve the module dependencies. Since requires can point to relative paths, they can omit file extensions, or they can even point to third-party dependencies that are stored in Node modules. To do so, Metro uses a similar algorithm than Node.js, but with some additional features. For example, to be able to resolve platform-specific files. So when you require view.js, it will either resolve to view.android.js or view.ios.js, depending on the platform that you're building for. Now let's see an example of how Metro crawls the module dependencies. Imagine that we have this entry point called index.js, which has 2 imports, to full and left pad. First thing that Metro does is to transform this code and remove new syntax features. In this case, it will transform imports into requires. Second thing is to collect the module dependencies. Here, both full and left path will get extracted, and kept in the list of dependencies array that we have at the bottom of the slide. Also, each of the requires gets transformed again, so paths are replaced by module IDs. In this case, for example, require foo gets transformed into require one. Finally, Metro wraps the transform code with a defined call, so the final output of the transformer can be concatenated directly to form the bundle. Once index.js has been transformed, each of these dependencies gets resolved. In this case, since foo is a relative require, it gets resolved to the file foo.js that is located in the same folder as index.js. In the case of leftpath, since it's a global require, Metro will look into node modules to find the leftpath folder. There it will read the package.json file, which contains a main field. This main field points to index.js, so then Metro will be able to resolve leftpath to node modules /defath/index.js. This same process is then followed for each of the new discovered modules in a recursive way. So if foo.js has two dependencies, bar and bus, they all get resolved, transformed, their dependencies get collected, and this goes on and on. Note that this algorithm also needs to handle cyclic dependencies, since these are allowed by the standard. In this case, Metro just stores the relationship between bar and foo, but it won't transform foo again, since that's not needed. Finally, the generation of the graph finishes once each of the modules of the app has been discovered, and this only happens once there are no more dependencies to crawl. So this was the generation of the graph. Turns out that this process is quite slow, and this is caused by the transformation of files, which is quite slow. That's because transforming files is a complex thing that involves a few complicated steps. The first thing is parsing JavaScript into AST, or an abstract syntax tree. This is expensive because of the dynamic nature of JavaScript. Then we have to mutate the AST, while keeping track of the modifications to be able to generate the source maps later. And the last part is to generate the JavaScript and the source map back from the modified abstract syntax tree. In fact, if we had to transform each single file sequentially every time that you reload your app, this would be insanely slow, so slow that you wouldn't be able to use React Native. So in order to keep things fast, Metro uses 3 different strategies. The first one is to not transform files at all. So Metro tries to avoid transforming a file whenever it can. And to do so, it uses a caching system. This cache is really easy to extend, since it has a layered architecture. With this, Metro can have multiple caches configured, and the caching system will go through each of them until one of them produces a hit. Adding a new cache layer is really simple. It's as simple as creating a class that has a get, a set, and a clear async method. With this, you can create your own caches that can do any kind of logic. In fact, at Facebook, we have one custom caching layer, which is an HTTP remote cache. This cache layer gets fulfilled by a continuous integration job that runs every time a commit gets committed into master. This provides significant improvements on initial build times, especially after pulling changes from the repository. There are still some situations where Metro needs to transform a big amount of files. For example, when modifying Bubble plugins or changing anything that has to do with the transformation pipeline. To speed up these scenarios, Metro parallelizes the transformation of files across CPUs. And to do so, it uses a package from another awesome project, JessWorker. This package is extremely easy to use. Here's an example. With a few lines of code, you can make any existing logic to run across multiple CPUs. For Metro, using JessWorker makes the transformation of files several times faster than when there is no cache. The third strategy to speed up builds is what we call the Delta Bundler. This is available during development, and this is what allows Metro to deliver sub-second reload times. With this, Metro keeps track of all the file changes that happen between reloads. Then, instead of regenerating the whole graph every time, it can just update the parts of the graph that have been modified. Thanks to this, Metro knows exactly what needs to be updated, so it can send to the client only the modules that have changed, which is way faster than sending the whole bundle. Finally, the Delta Bundler is enabled right now by default on Android devices, and we're currently working on adding support for iOS. Let's see how this works. Imagine that we have the following dependency graph. The first time that the client requests a delta from Metro, Metro will send all the bundles, since there is no previous state. Now, if we modify foo.js, when the client reloads, Metro will only send the modified version of foo instead of the whole bundle. Then imagine that we add a new require in bar.js that points to a new file called new.js. In this case, Metro will detect this change and will send both new.js as an added file and bar.js as a modified file. Also, if new.js had also other dependencies, they would be added as added files. Now imagine that we add a new require from foo to new. In this case, Metro will only send foo.js as a modified file, since new.js is already in the bundle now. A module can also be removed from the bundle. This only happens when it's no longer required by any other module. Here, if we remove the required to new.js from both foo and bar, Metro will tell the device that foo and bar have been modified since we modified them, and new.js have been deleted. So to recap, Metro has been designed to be fast and scalable. Our goal is to provide sub-second reload times, even for really large applications. And to achieve that, Metro uses these three techniques that I just described, which speeds up the generation of the dependency graph. Now that we have the graph, let's see how the process of serializing it looks like. The serialization phase is what happens just after the graph has been generated, and it takes the graph as an input and can return anything, buffer, an array, or even store files to disk. Metro has many serializers, for example, for creating bundles, for creating source maps, or even for storing assets into disk. Let's see the most common serializer, which we call the plain JavaScript serializer. And this one is what it actually stores the same bundle that we saw at the beginning of the talk. The bundle here is created by traversing the dependency graph to get all the modules in the app. Then we concatenate them to form the bundle. Also, you can see how the runtime and the startup code get included in the bundle, one at the beginning and the other one at the end. Note that this process is really fast, since it only involves the string concatenation. In fact, this only takes a few milliseconds to do, even for really large bundles. Now let's take a look at the random access module serializer, or RAM bundle serializer. This is only relevant to React Native. This one produces a binary bundle, as opposed to the plain JavaScript bundle that we just saw, which was a simple string. This format contains the same pieces as the plain bundle, but instead of having the modules concatenated, they are stored in the following structure that you can see in the slide. The first thing on the RAM bundle is the header, which is a magic number that stands for FB0 bundles, as you can kind of read. Then we have the table of contents, which is a lookup table to find the modules inside the bundle. They contain the offset of this, and the length of each of the modules. After this, there is the start part, which contains the runtime and the startup code. This is what is going to be executed when we start the application. And at the very end of this binary format, we have the list of modules, each of them separated by null characters. To understand the benefits of RAM bundling, let's see how a standard bundle gets injected into the JavaScript virtual machine, so we can compare it to a RAM bundle. In the case of a standard bundle, this is very simple. The whole bundle gets injected as a string once during startup. If the bundle is really big, this can be really slow, because the virtual machine has to parse all the JavaScript, and this consumes a lot of memory. On the other side, with RAM bundles, only the runtime and the startup code gets injected on the startup. And as we saw before, both of these parts are quite small, so this is usually fast and improves startup times. After this has been done, each of the modules gets injected into the VM lazily, as they are required, which means that code that is not used is not even injected into the virtual machine. But how do modules get lazily injected? If you remember for one of the first slides, this is the require function, which had a check to see that if the module ID had not been registered and throw an error. For RAM bundles, the throw error statement gets replaced by a call to native require. And native require is actually implemented in the native side of React Native. This function first finds the module ID in the lookup table. Then it injects that module. Then it gets the offset of that module, and it goes find it in the list of modules. Once it gets it, it's injected into the JavaScript virtual machine. And once the model is injected, it gets automatically registered in the runtime, since it's wrapped around the __ decall that we saw before. After this happens, the execution of the required function continues, and then it can find the module has been registered. So these are the RAM bundles. To recap, with RAM bundles, only the models that are being used are injected into the VM. This provides significant improvements both in memory usage and startup times of React Native applications. Now let's talk a little bit about inline requires, which is somehow related with RAM bundling. Most of the times in JavaScript, important requires are defined at the top of the bundle, as you can see in this code. This means that in a typical application, most of the modules will get required and therefore evaluated during a startup. This is not good, especially for RAM bundles, since this basically means that all the modules will still get injected into the VM during a startup. And this will defeat all the purpose of a lazy evaluation. In order to avoid this, Metro has an option to enable inline requires. This is a bubble plugin that moves each require statement from the top to the place where it's being used. And this allows to have proper lazy evaluation of modules. And when it's combined with RAM bundles, it also gives lazy parsing of their JavaScript code. There is also another benefit of inline requires, and it has to do with that code elimination. Imagine that we have the following code, where there is a debug function that is called inside a def statement. When this model gets transformed for production, the def condition gets removed, but the required statement remains there. This means that Metro will still add the debug.js module in the bundle, which is not good. When inline requires are used, the required is moved inside the condition, so the transformer is able to remove the required statement when it removes the def condition. This is why the debug module does not even get collected as a dependency, and it never gets included in the bundle. And this was all for today. But before we finish, if you want to take two practical advices from this talk, here they are. The first one is that if you have slow build times, consider using a remote cache. This will speed up initial build time substantially. There is documentation about how to do this in the Metro website. The second thing is that if you want to improve startup times of your apps in production, try out the RAM bundling, especially with inline requires. This will probably have an important impact in the startup times of your app. Again, there is information about how to enable RAM bundles in the React Native website. And this is all. Thanks you everybody.